Welcome everyone to this lecture series on trying to tackle that MNIST digits dataset with just a normal artificial neural network. This will help us get an understanding of the actual dataset and then later on see the limitations that an artificial neural network has compared to a convolutional neural network. Let's get started by actually exploring the data and showing you how to load it. Let's head over to the Jupyter Notebook. Okay, we're going to begin with a couple of imports. First, we will import torch. And since we'll be building a network later on, we'll say import torch.nn as nn, along with import torch.nn.functional as f. So we'll load those in, and then we're also going to be loading in some data. And since this is image data, we'll also be using the torch vision library, which is already included in the environment and should be installed if you use the environment and followed our install and setup lecture. Let's go ahead and say from torch.utils.data import data loader, and then from torch vision import datasets comma transforms. So after that, we'll just import kind of some of our standard ones, like numpy as np, import pandas as pd, and some of these we may or may not use, but it's nice to have them right at the top. Later on, we'll be performing some metrics analysis, so we'll also import confusion matrix from sklearn. And then finally, since we will be visualizing a little bit of this, we'll say import matplotlib.pyplot as plt, and then matplotlib inline. And you can always copy and paste all of this from our provided lecture notes. So now the first step is to actually load in our MNIST dataset. And PyTorch makes the MNIST dataset available through the Torch Vision library. And the first time it's called, dataset will be downloaded onto your computer to whatever path you specify. So you can specify it to be downloaded into our data folder, and we'll show you how to do that. So for this exercise, we're just going to need to convert images to tensor, and as part of the loading process, we can actually apply multiple transformations, things like reshaping, converting to tensor, normalization, etc. All we want to do is we actually want to grab these MNIST image files and then convert them to PyTorch tensors. And so the way we do that is I'm going to define a variable called transform, and then recall that we imported from Torch Vision's transforms. So what we'll say here is transforms with an S dot, and if you hit tab here after you've imported this and ran it, you should see kind of a bunch of different transformations you can do. Things like resizing, scaling, vertical flips. We'll talk about those later on when we actually work with your own image files, things like JPEG files or PNG files. For right now, we just want to make sure that when we load these images, we're loading them in as tensors. So the one we're going to use is called toTensor, and then open and close parentheses, and there's our transform. So let's go ahead and load in the training set. We will say train data is equal to datasets.mnist, and if you do shift tab here, you'll see a bunch of options, so I can expand on this. You get a root option. That's where you actually want to save the file to, or the MNIST data to. So we would recommend that you just save it to a data folder. And if you're, depending on where you're located in your notebook, if you're located in the exact same location as our lecture notebook, that would be up one directory and then into the data folder. And then we want to say train is equal to true, since we just want the training set here. We'll say download is equal to true, whoops, since we want to download it. And then we'll say transform is equal to transform. All right, so we're loading in that data set into this folder. Obviously, you can load it into any folder you want. Depends on what your situation is on your computer. We want to specify that we want the training data, downloading it, and then we want to apply this transform that transforms everything to a tensor. So we'll go ahead and run that. And my data actually happens to already be there, so this was basically instant. And if you downloaded our zip file the same way I have it right now, then this should also just kind of be instant for you. If you're doing this to any other directory, it'll take a little bit of time to download, and it'll report back something like number of data points 60,000, split is train, root location, etc. So it'll report back a little bit to you in case you are downloading it for the first time. And then we want to do the exact same thing, except now for the test data. So we'll say datasets, MNIST, root. I'm also going to put this just into my data folder. And then we say train is equal to false, which basically implies that we want the test set. Then we'll say download is equal to true, and we're going to do the same transform. We'll say transform is equal to transform. go ahead and run that. And again, if you're using it in our exact same data folder, it should essentially be instant. And you can check out these data points now. So we'll say train data. So training data reports back. Here's the data set, 60,000 training points. And if we look at test data, we see here it's 10,000 test points. Okay, so let's go ahead and just examine a single training record so we can kind of make the connections between our MNIST theory lecture to what we're actually looking at. So if I take a look at the type of my train data, it's going to be this torchvision.datasets.mnist.mnist. So it's actually kind of a very specific torch vision dataset type. Now what I can do is I can actually index off of this and I get back this tensor. So essentially this torchvision.dataset MNIST data type is a bunch of tensors kind of organized together. So here we can see a training data record. So this calls the first record from the train data. And what's interesting about this, it returns a 2-item tuple. So if I were to actually check the type of this, it's a tuple type. And so the first item is the 28 by 28 tensor representing the image. The second item is the label. So if we actually run this again, so this first item, you can see here, there's a first parentheses that indicates that it's a tuple. So here we have this tensor, and that's actually the first image, so it's 28 by 28. And if you scroll all the way down, you see right here, this little number 5, that indicates the label, that should be a 5. So let's check it out. In fact, let's actually do a little bit of tuple unpacking. We'll say image, comma, label is equal to train data 0. Run that. And then let's check out this image. So we can check out the shape of the image, and we can see right here it's 1 by 28 by 28. And the reason we have 1 here is because this is a grayscale image. So there's essentially just a single color channel for black or white. So 0 would be one extreme value, and then 1 would be the other extreme value. And also keep in mind that depending on where you download MNIST dataset from, sometimes they're scaled from -1 to 1 instead of from 0 to 1. So just keep that in mind. And here we can see the 28 by 28, just as we previously discussed. And then the label, well, that's just a single number representing that it should be a 5. And so let's actually visualize this with matplotlib. We will say plt imshow, and imshow is designed to, if we take a look at here, it's designed to take in this x, and what it does is essentially displays an image. So just a 2D regular raster image, essentially just rows by columns. Now we have a little slight problem here. Right now we can see we have this extra channel indicating that's a black and white image, when really we just need to reshape this as a 28 by 28. We don't really need this kind of empty extra dimension. So what I'm going to do is I'm going to say image dot reshape, and we'll reshape it as a 28 by 28, essentially just dropping off that information that it's a grayscale image, since we kind of already know that by default. And then if we go ahead and run this, plt imshow, you should see something that looks like this. Now keep in mind, matplotlib has a default color mapping. So this default color mapping is a color mapping called viridis. So if you spell it out, it looks like this. This does not imply that the actual image itself, if you were to load this into Photoshop or something, would be yellow and purple and have these greens. It's essentially just mapping the raw values, 0 or 0.2157, etc., to some sort of color scale. And the default color scale goes from like a dark purple to this kind of lighter yellow color. And the reason for that is because for colorblind people, it's really easy to visualize those differences. So that's why that's the default coloring. But I don't want you to get confused here. This is definitely a grayscale image, as we can just confirm by the values only going from 0 to 1 across a single channel. So how do we actually view this in grayscale? What we can do is provide a color mapping. So we can say CMAP is equal to, and then if you look up in the matplotlib documentation, they have a bunch of different color scales. So gray basically goes from black to white, and if you want to reverse this, the color mapping to use is gist_YARG. So run that, and essentially you get the reverse color mapping, because it's really up to you what color scale you want to use for these numbers that go from 0 to 1. So that's why you can kind of edit out those color mappings. But the main thing to know here is when it comes to the raw data, we just have values that go from 0 to 1, which is essentially a grayscale image. Okay, so now that we understand what the actual data looks like, and we can kind of confirm here, this does look like a 5, what we want to do is understand how to load in batches with the data loader. So right now, our training set contains 60,000 records. And if we look ahead to our model, we have 784 incoming features, since we're just using a normal artificial neural network. And later on, we'll go ahead and set a hidden layer of 120 neurons with another hidden layer of 84 neurons and then 10 output features. So if we include the bias terms for each layer, we're going to have a lot of parameters. So for this reason, it makes sense to load in training data in batches. So what we're going to do here is we're going to essentially grab subsets of these 60,000 images and then load them in instead of loading in all the data at once. So we'll say torch manual seed. And the reason for this is because since these batches are essentially going to be taken from the randomly shuffled data, we want to make sure that my random shuffle that I'm filming right now is the same as your random shuffle. So we can do that by setting a seed. And again, as always, 101 is just kind of an arbitrary choice of a number. So then what I'm going to do here is say train loader is equal to data loader. And I'm going to pass in my training data, my batch size, and this is where you can kind of play around with it, but we'll go ahead and use a batch size of 100, meaning out of those 60,000 images, I'm going to be feeding 100 images at a time as a batch into my network. And then we'll go ahead and say shuffle is equal to true. And the reason we want to shuffle is sometimes certain data sets are organized or sorted. So maybe it would show all the 0 images, and then it'll show all the 1 images, and so on. What I don't want to do is just grab all the 0 images first in batches of 100, then grab all the 1 images in batches of 100, and keep training the network that way, because that will kind of screw up the network to first get really good at zeros, and then suddenly the 1s come in and it won't really learn those that well since it was just trained on zeros. What I want it to do is be able to generalize to all those digits between 0 and 9, which is why I want to shuffle that training data. Now when it comes to the test data, since I'm not really going to be adjusting my weights or biases there, that doesn't really matter as far as the shuffling. So what I'll do is for my test loader, we'll say that's equal to data loader, and we'll just pass in our test data. We'll pass in a batch size, and for this you can then make a larger batch size since you're essentially just going to pass in a bunch of images and classify them. So we'll say batch size is 500, and here we'll say shuffle is equal to false. Okay, so keep in mind that in the cell above, train data, that is a PyTorch dataset object. So it's an object that supports data loading and sampling. And that batch size is the number of records to be processed at a time. And keep in mind, if it's not evenly divisible into the dataset, then the final batch would contain that remainder. And setting shuffle to true means that the dataset will be shuffled after each epoch. All right, so to finish off this lecture, what I want to do is just visualize a little portion of what the train loader would actually give back. We won't do 100 images, we'll just do a little subset of that. But first we actually need to then grab a batch of images and then display them as a grid of numbers along with their labels. And one way I can do this is, luckily, I can say from torchvision.utils import, and there's this really nice make grid functionality which shows you a grid of images. And then what I'm also going to do is I'm going to print out the labels right on top of this grid. And to make sure the spacing lines up correctly, I'm going to set some print options for NumPy. So you don't need to understand what this line of code is doing, besides the fact that it's just basically formatting so that this looks nice as we're recording it. So it's just essentially making the spacing of the actual NumPy array a little wider so it lines up with the grid. You'll see what I mean once we actually print it out, but you don't need to understand this kind of complicated print option since you don't really need to edit it in real life. This is really just for filming this and making this look nice. So the line that is important here is this make grid line, since we're going to be using that function in just a second. Now what I want to do here is actually just grab the first batch of images. So I just want the first batch. And the way we can do that is I can say for images labels in train loader. And if we think about this right now the batch size is 100, right? So if I were to run this for loop, since there's 60,000 images and then the batch size is 100, then this for loop would essentially go through around 60 times. Because since we're feeding it in 100, there's essentially 60 total times we can feed in 100 batches. However, I actually just want the first batch. So what's a neat little trick here is right after we run this very first instance of grabbing that kind of first batch of 100, I'm just going to break out of this for loop. So if you run that, what's interesting now is if you take a look at images, images is now this tensor of just that first batch. And if we check out its shape, it's essentially 100 images, grayscale images, so there's only one color channel, and they're 28 by 28. Notice now we have kind of this 4D tensor, where it's describing that we have 100 images, there's one color channel, and they're 28 by 28. And if we then check out the labels, and check out the shape here, this is then 100 corresponding labels. So that's where we break immediately after running the kind of first for loop, because we just want the first batch. And this is a little bit of unusual syntax, but basically it just allows us as kind of a quick trick to grab the first batch. And so for the rest of this code, I'm just going to copy and paste this from the lecture notebook. And what I'm going to do here is copy and paste from the view a batch of images cell in the lecture notebook these lines of code. Essentially what we have here is we print out the 12 labels. So in fact, if I kind of separate this out and just run this, you can see here we have the labels being printed out. You'll notice the spacing is quite wide between them, and that's because of what we did up here with the set print options. So you can always reset your kernel and delete this line in case you wanted to print out as a normal NumPy array. And then if we print out the first 12 images, let me go ahead and put this all back in the same cell. So we get this nice formatting here. So we print out those first 12 labels using NumPy. And then what we're going to do here is we print out the first 12 images. Recall images right now, it's 100 of them. I'm only going to grab 12. So we'll grab 12 of them here. And then the way make grid works, you can define the number of rows. Unfortunately, you can't define the number of columns. So we'll say we have 12 rows, and then we'll say PLT figure. You can set a fig size here to make the image a little larger so it looks up a little nicer here. And then finally, we need to transpose the images in order for PLT imshow to understand it. Recall that up here we had to do a little bit of reshaping. Essentially the same idea still applies. So right now, if we take a look at what each of these dimensions stands for, it's number of images, the color channel, and then the width of the image and the height of the image. PLT imshow expects these to be in a slightly different order. It expects it to be width, height, and then color channel. So right now we have, since we're just feeding in kind of images one at a time here, out of 12 of them, it has color channel, width, and height. Essentially, matplotlib needs it to be width, height, and then this color channel needs to come all the way at the end. So it can do this with a little bit of a NumPy trick called np transpose, where you tell it, okay, grab in the index 1 and put it first. So if you go 0, 1, that's 28, and it says, okay, grab index 2 and put it second. So 28 now goes here, and then grab index 0, which was that color channel, 1, and then put it at the end, which effectively changes it from color with height to width, height, color. And don't worry too much if you don't understand all of this. This isn't really pertinent to the course. It's really just to make this look nice. So we run this, and then we can see the corresponding labels, 0, 5, 7, 8. And then notice right here, some of these are actually quite sloppy. So if you notice this one, this particular 6, that's a really sloppy 6. So we shouldn't be surprised when the network maybe labels this one as a 4 or something, because to me it almost looks more like a 4 than a 6. So this is also important to understand the complexity of what the network and later on the convolutional neural network are going to be able to do. So even a human will probably miss some of these numbers. Okay, so we can see here we're able to load up batches of the data and then visualize it. Coming up next, we'll go ahead and define our multi-layer perceptron model, count the model parameters, define a loss function and optimizer, and then we'll also end up flattening out the training data so it fits into our flat artificial neural network with 784 neurons. And then after that, we'll train and evaluate the model. Thanks, and we'll continue this in the very next lecture.